This is Rich Taylor, Miami University. The topic of this presentation is functional groups, which really forms the framework by which most of organic chemistry is considered and studied. The reason why we group things by functional groups is the simple fact that there are a huge number in the billions of organic molecules and nearly an infinite number of possible organic molecules. In order to make sense of the reaction, we can't learn reactions molecule at a time. Luckily, we can group molecules by means of their structure into groups that display similar chemistries. Those are the functional groups. So in general, then, we're going to study organic reactions by means of their functional group because the functional group will determine most of the chemistry that an individual molecule will undergo. The added bonus is this is also the basis by which you will learn organic nomenclature. If you think about reactions and what chemists do, they're generally taking small, simple molecules and elaborating them into more complex, more valuable species. That could involve making carbon-carbon bonds. We call that building the framework. Many of the reactions that build a framework require certain functional groups. The functional groups may just be there to enable you to do the assembly. Afterwards, you're going to need to adjust those functional groups. Those adjustments of functional groups could be reductions, they could be oxidations, they could be neither. And so throughout the general sophomore organic course, you're going to go through the functional group chemistry and examine the reactions of that group that lead to allow you to build up molecules by the considerations listed above. So the objective of this presentation is to learn the major functional groups. We're going to group these functional groups by what I call oxidation level. And I call it oxidation level because it's not exactly the same as oxidation number. This is going to allow you to group reactions easily, so we'll not only group functional groups, but we'll be grouping types of reaction, and is also going to give you a viewpoint that's going to help in nomenclature. Finally, we'll want to be able to characterize reactions as oxidation, reduction, or neither. Let's start off by considering the alkanes. That's the least oxidized functional group, has only carbon and hydrogen single bonds. There are alkanes and cycloalkanes, but in general they're going to have the same chemistry unless the ring size is very small, and they're generally going to be less reactive than all other functional groups. The reason why I like to talk about oxidation level rather than oxidation number is that there's a subtle difference from one alkane carbon to another, and that relates to the number of carbons versus the number of hydrogens that are attached to that particular carbon you are looking at. We call primary carbons ones that are only attached to one other carbon. We call secondary carbons ones that are attached to two carbons, and then of course tertiary and quaternary would follow. If you think about oxidation number, these kinds of carbons have different oxidation numbers, but we generally consider them all at the same oxidation level and don't talk about these kinds of differences in terms of redox. Here are some examples. If you look at this structure, you can see that there's one primary carbon. It's bonded to only one other carbon. This carbon's tertiary. It's bonded to three others, and the others around the ring are all secondary. Likewise, down here we have primary, primary, three more primaries. Here's a tertiary. It's bonded to three other things, several secondaries, and here is a quaternary. It's bonded actually to four other carbons and has no hydrogens attached to it. This is the lowest oxidation level. In order to increase the oxidation level, you're going to take alkanes and oxidize them. There are two ways to think of oxidation when you talk about organic molecules. A material is oxidized if a molecule of hydrogen is removed. Make sure that you think of that in terms of H2 and not H+. We need to remove hydrogen for it to be an oxidation. Substitution of a bond to hydrogen or carbon to a bond to heteroatom is also classified as an oxidation. What's a heteroatom? If it's not carbon or hydrogen, it's generally a heteroatom. And so we particularly group halogen, oxygen, sulfur, and nitrogen there. So oxidation then can be defined as adding bonds to heteroatom or removing hydrogen. Reduction is reducing the number of heteroatom bonds or adding hydrogen. As we look at our mock-ups of the functional group, it's important to understand what we mean by X and R. X is typically the term we use for any generalized halogen, particularly chlorine, bromine, or iodine. In general, those chemistries are going to be fairly similar, and so sometimes you just put X because the chemistry will be the same regardless of the halogen. Fluorine can be a little bit different, and sometimes we'll exclude fluorine from the X designation. R is any collection of alkyl chains. Essentially, these are groups of carbons that are less reactive than the functional groups that we're going to look at, and so typically the R group can be any kind of carbon thing, and it's going to be just along for the ride in most reactions. So when we write generalized structures, we'll put in R because the general configuration of carbons out yonder there are going to be insignificant. Sometimes R can be a hydrogen, sometimes not. It really depends on the context you're using. But it's always collections of carbons can always be denoted as R. So we can look at the next higher oxidation level after alkanes, and those are ones that display one bond to heteroatom. So the heteroatom could be oxygen, and if the oxygen that's attached to your carbon is bonded to a hydrogen, we call that to an alcohol. If there are carbons flanking on both sides, we call that an ether. Notice when I use R and R prime, I'm trying to indicate that those two groups need not be identical. If the nitrogen is the heteroatom, then you have an amine. If it's a halogen, it's an alkyl halide, alkyl bromide, chloride, or iodide. If it's an SH instead of an OH, we call that a thiol or a mercaptan. The ether analog in the sulfur species is called a sulfide. Those are all at the same oxidation level because the carbon that's bonded to the most number of heteroatoms is bonded to only one. If we need to, since we need to relate bonds to heteroatom to addition to hydrogen, what we will find when we try to integrate the two is that alkenes, functional groups that have C double bond Cs, also belong at this oxidation level. And so if we look at the following oxidation and reduction type equations, we can see that this reaction, we take a species where every carbon is at the alkane level and transform it to where one carbon is now bonded to an oxygen. We've increased the number of bonds to oxygen, that's an oxidation. Here we have an alkene transformed to an alkane. To go from here to here, you need to add hydrogen. Adding hydrogen is a reduction. If we take this alkyl halide, bromide, and transform it into the amine, we take a carbon that's bonded once to heteroatom and continued to have it bond to one heteroatom. All we've done is change the heteroatom. So that's neither an oxidation nor a reduction. That's a transformation of a functional group without changing oxidation level. If we go to two bonds to heteroatom level, we can see the following sort of molecules. One of the most common configurations then is a C double bond O that's sometimes called a carbonyl group. At this oxidation level, you can have aldehydes and you can have ketones. Notice in this case, R prime is a carbon thing for it to be a ketone. If it's a hydrogen, we call it an aldehyde. We make that distinction here because the chemistries of those two things are different enough that we're going to want to classify them in that way. The other species that's most important to understand at this oxidation level is the triple bond with carbons. That's called an alkyne. These others are potentially important species, but a little more rare. C double bond N is an imine. If instead of a double bond to oxygen to make our two bonds to oxygen, we have two bonds to separate oxygens, we can have what's called a hemiacetal or hemiketal, acetal or ketal. We can marry heteroatom with double bond, and at that oxidation level then is going to be what we call an enamine or an enol, and those sorts of species are also known either as compounds or intermediates, but the ones you want to really pay your attention to are the big three here. Continuing to look at equations, you can see that this first reaction, the alcohol going to ketone, one bond to oxygen becoming two bonds to oxygen, that's an oxidation. Ketone going to an alkane, we had two bonds to oxygen going to no bonds to oxygen, that's a reduction. And in this species we have a ketone going to a ketal, two bonds to oxygen, the carbon that was transformed still has two bonds to oxygen, so that's neither. Moving on to 3 bonds to heteroatom, we now have species that you probably have seen before. Here's a carboxylic acid, 3 bonds to heteroatom, 2 to 1 oxygen, 1 to another. The OH, if we transform the OH into an OR prime like we did with ethers, that species is now called an ester. This is an acyl chloride where we trade the OH for a halogen. If we have a nitrogen there, we have an amide. Triple bond to nitrogens at that oxidation level. That's 3 bonds to heteroatom as well. That's a nitrile. This sort of species is also going to be important. It's an anhydride. There are actually 2 different carbons going to 3 bonds to heteroatom. Look at that name, anhydride. You can sort of see that you can get from carboxylic acid to this by bringing 2 together and losing water or losing hydrogen oxide. So anhydride is the name that's given to that. And so if we look at some interconversions, this should be getting familiar to you now. 3 bonds to heteroatom going to 3 bonds to heteroatom. Nitrile to amide is neither an oxidation nor a reduction. 3 bonds to heteroatom into carboxylic acid going to an alcohol with only 1 bond to heteroatom. That's a reduction. Accompanying this particular presentation is also a master handout with a large number of functional groups, all grouped by oxidation state. The skills to master are to identify the functional groups designated as being the most important ones, and to acquire the ability to classify reactions as oxidation, reduction, and neither. 2 final points. I want to make sure we talk about multifunctional compounds and also how this relates to nomenclature. First off, let's consider this molecule. This has 3 bonds to oxygen, but what's important is it's not 3 bonds from the same carbon to an oxygen. This is not a carboxylic acid. This is an aldehyde at one end, and it's an alcohol near the other end. That is a multifunctional compound. It doesn't display the chemistry of carboxylic acids. It displays the chemistry of aldehydes and the chemistry of alcohols, depending on what kind of reactions you do. And multifunctional compounds make organic chemistry complicated, but it's also very important in terms of important compounds that have those characteristics. Basics of nomenclature. I'm not going to go through all of nomenclature at this point, but want to give you sort of the strategy that the IUPAC uses to give names. It consists of 3 parts. There's a prefix, which identifies your substituents. There's a root name that talks about what we call the main chain, and then there's a suffix which tells you what functional groups are there. The real key to doing nomenclature properly is to learn how to read from right to left, because that's how you put things together. And so the steps for naming the compounds are to first identify the top priority functional group, and that will be your suffix. That's the carbon with the most bonds to heteroatom. So if it's multifunctional, go for the one with the most bonds to heteroatom, but always be looking for heteroatoms. And the name of the functional group is actually going to tell you what that suffix is. A ketone is going to have an ONE ending. An alcohol is going to have an OL ending, and you'll learn these things as you go along. In general, you can only have 1 suffix. The exception to that is "-ine" and "-ine", which you can embed in the middle of your name and make a second suffix, so you can have an "-ine-one" or an "-ine-ol", but in general, all other functional groups can't be a second suffix. They must be named as a substituent and a prefix. So, you name the top priority functional group. The longest chain, what we call the root name, that includes the functional group is going to be the main name in the middle. After you've identified the functional group and the main chain, you're going to array all of the other substituents that aren't part of the main straight chain and use those as a concatenation of prefixes in alphabetical order and for numbers for their position along the chain. At this point, you're not really ready to name organic compounds, but that's going to be the strategy that you're going to see again and again as you develop these kinds of skills. And so, at this point then, you should be able to begin to see how organic compounds are going to be characterized, and if you look through the table of contents of your textbook, you're going to start making good sense of how things are organized.